So this is the lecture, and why is it not coming up here? Just watching. So we got to cool. We got to series and parallel inductors. I was kind of going quickly here, and I was thinking we should wrap this up. So we were learning about inductors and how we're doing these the relationship between voltage and current for inductors and capacitors are differential equations, so that brings an interesting element into the class. And we talked about how the inductors, in the steady state, they're like a short circuit. And we found the energy, right? The energy in an inductor depends on the instantaneous current. So that's 1/2 Li squared for an inductor. And then we were kind of rushing, and we sort of talked about, series and parallel inductors. The inductors behave like resistors, so they add up when they're in series. And but capacitors behave like conductance, G, so they add up when they're in parallel. And then you can use these voltage and current divider formulas, equations as well. So, I'm in a pickle here. Let me see. Oh wait, I have. So we stopped at this line, right? We didn't solve this problem, right? We said, this is example 5. Given that I of t equals 8 times 1 minus e to the minus 10t milliamps. We're supposed to find v of t, v1 of t, v2 of t, I1. We're supposed to find every circuit variable in there because these are different. This is a different world here, working with inductors and capacitors, right? So we are going to solve this problem. And so basically what we're saying is we know the current going into the positive terminal of this network of inductors, right? And we're supposed to find all these other things. Well, the thing is, we know that the voltage is going to equal the voltage across the whole thing, right? If we know the current I, and we know this thing, which is a network of inductors, can be reduced to an equivalent inductance. Like we can reduce resistors into a single resistor, we can reduce this thing to an equivalent inductance, right? So we can say V equals L equivalent times di dt. And we can say that, you know, L, and this would be our L equivalent, right? And we have this I going in there. I don't know what that noise is. And so basically, right, if we know what L equivalent is, we can find the V of the whole thing, right? So that's the main issue. So what do we find? What's L equivalent here? What's can anyone tell me what that is? Just by doing it by inspection, it's 5, right? Why is it 5? Isaac, do you have your notes from yesterday? We're continuing the lecture. It is 4 parallel with 12, just like resistors, that's going to be 3 henries, and you're adding that in series with 2, so that's 5, right? So L equivalent equals 2 henries plus 4 henries parallel with 12 henries. So that's going to give us 2 henries plus 3 henries. So we're finding V, it's going to be 5 henries times di dt. That's the relationship for inductors, right? V, 5 times di dt. And we know I is 8 times 1 minus e to the minus 10t, so we just differentiate that thing. We should be pretty good at that. So that's going to equal it's going to equal 5 times, well, the 1 just goes away when you differentiate that, right? But then you've got minus 10 times minus e to the minus 10t. So that's going to be 80 e to the minus 10t, right? 80 e to the minus 10t. Right? So then that's going to equal 400 e to the minus 10t. And since this is in milliamps, then this is going to be in millivolts. And so then, well, once we know the current there, we can then sort of find V1 of t equals, well, it's the same I flowing into V1 as is flowing into L equivalent, right? So that same I going through a 2 Henry resistor is just going to be 2H times di dt. And that's going to equal 2 times that same derivative, 80 e to the minus 10t. So that's going to be 160 e to the minus 10t You know, now we've got functions of time for our currents and our voltages. Keep track of those things. And if V1 of t is 160, what is V2 of t? What does V2 of t have to be kind of by inspection? 240, right? Yeah, it's got to add up to 400. So e to the minus 10t millivolts. And so we found V of t, V1 of t, V2 of t. What about I1 of t and I2 of t? If we know what V1 of t is, then I of t would be, we sort of have to integrate that, right? To go the other way, we'd have to say I of t is the integral of V1 of t. But the current divider equation can also be used in this case. So this is kind of interesting. So we can do the current divider equation here. And since we know what I is, I1 should be 1 over the inductance times I over 1 over the inductance of itself plus the sum of the reciprocals of the inductances. So that equals 1/4 over 1/4 plus 1/12 times 8 times 1 e to the minus 10t. So I1 would then equal, that equals 6, basically 6 times 1 e to the minus 10t. And I2 similarly would be 2 times 1 e to the minus 10t. Sorry, 1 should be 1 minus, sorry, 1 minus e to the minus 10t. Yeah, if you don't like that, then you could say, well, you know, I1 of t also equals the, you know, the integral of, it's 1 over L times the integral of V1 of t dt. Plus some constant as needed. And, but that constant is sort of being provided automatically by these current divider formulas. So just leave it as that. Yep.
So when you solve for I1, how do you get from step 1 to step 2? How do you get from 1/4 over 1/4 plus 1/12 times I?
Well, because I is given above as 8 times, well, that's the source. So it's a current divider, right? So I is the source that's being split between these two pathways. And we're using the current divider equation to find out how much of I is going. And so this is our I. This is our source. Oh, it's 1 minus. Sorry, I was blanking out there.
And then what you just 1/4 plus 1/4 times 8 times 6.
Supposedly, yeah. Let's try that out. So, so let's see. 1/4 over 1/4 plus 1/12. That's 3/12, right? This is let's do it a little side here. So 3/12. Do it up here, maybe. Yeah, 3/12 over 3/12 plus 1/12 is 3/4. Yeah. Mm-hmm.
And the other way to do that is instead of writing 1/4 divided by 1/4 plus and 12, you do the other inductor divided by the sum of the two. So you do 12 divided by
Yeah, you could also do, yeah, I like it doing that one. When you just have two of them, you know, it's sort of simpler to just say it's 12 over 12 plus 4. Oops, not 14. Yeah, so any questions on that? That's so the purpose of this sort of this assignment that we're doing is just sort of getting us exposed to the these new relationships, the new VI relationship between you know, for capacitors and inductors. It's a different world where you've got time signals now. You've got to do, you know, you have to do differentiation. You have to do integration, that kind of thing. So these are the relationships then between all these, and the basic sort of Ohm's law relationships between resistors, inductors, and capacitors. It's kind of helpful to see them all right next to each other. Power equals V times I, and energy is the integral of power dt. But you know, so for resistors, you sort of have to do an integral of the power to find the energy dissipated over time. But for inductors and capacitors, the energy is instantaneous, like they're storing energy instantaneously. The resistors don't actually store energy, they're just dissipating it, right? But inductors and capacitors will actually store it. And so the energy indication here is how much is currently being stored in the inductor. If you know what the instantaneous current is, the energy it falls out immediately. It's 1/2 Li squared. And same for capacitors. And let's see if this makes any sense. The comparison with mechanics. Let's see what we have here. This is great for mechanical engineers because you know, these are the typical equations. So you know, with mass, we have F equals m times du dt. That's change in position, I guess, right? So it's or is that, no, it's velocity, right? Wait, what is it? What's m du dt? It should be m dv dt, right? And we have spring constants. I guess I'm not sure the point of this slide. It's really there are interesting mechanical analogies of here, but for here, but it's yeah. I should probably just delete this slide. And I guess the analogy is, let's see here, the electrical, mechanical, rotational. I guess you can kind of go through these different domains. So yeah, that kind of makes sense that electric potential is kind of like a force, and that in rotational sense is like a torque. Current is kind of like a velocity, I guess. So I didn't realize those relationships, but I guess they're there, which is pretty cool. Charge is like position, weird, and rotation because of the integration that's going on between these, I guess. And yeah, not being a mechanical engineer, this is actually a little bit lost on me. So, since I don't know this, I'm just going to delete this rather than trying to figure it out myself. Actually, it would probably be interesting to try to figure it out. I should probably study this and get back. One of the interesting things I had, which is cool, there are these interesting mechanical analogies with circuits, and like I mentioned earlier, like a capacitor is kind of like a jar of rubber bands, or you can think of it as like a spring. The more force you put, the more stuff you can, charges you can stuff into it. And inductors are kind of like flywheels. Mechanical analogy of a flywheel is it wants to keep spinning. A flywheel is like a heavy disc that you put, like they have in cars, to keep the engine spinning smoothly. And you know, once you get the thing spinning, it wants to just keep spinning. With inductors, once you get current flowing through an inductor, it wants that current to keep flowing, and it's going to try to, like if you try to change the current, it's going to try to kick back enough voltage to keep the current going the way it was. It doesn't want to change it. So that is the lecture. Any questions then? Before we start the problem session? We can start a few problems. Yeah, Isaac? You mean this problem, example 5 here? Yeah, this one's kind of tricky, right? And you have to kind of go back and forth. You got to figure out what you know and everything, and then how you can extrapolate to the new thing. Well, you start off by finding the overall V by thinking of the equivalent inductance of that whole network. Because if you know the current going into it, the equation V equals L di dt will actually tell you what the voltage is. That's the first step, is to sort of find the overall voltage at these terminals using the equivalent inductance of the whole thing. And then once you have that, you can then sort of break that down. Well, you also know V1, you know, because that same current is flowing through the 2 Henry inductor. And now you know V1, you can also figure out what V2 is, because they have to add up together to V. And you know, you're just building what you know and just sort of, what do I know? And then what can I figure out from what I know? You know, one step at a time. Follow?
Yeah. How do you know if it's a pattern where the equivalent element is placed? Like where either there you have the L equivalent across in the voltage terminal, would it change it? Or how do you know it would be there if it was like adjacent to it?
How do you know L equivalent would be across the terminal that V is at? Well, I mean, we're intentionally, it's just the same reason why, you know, when you have a network of resistors, we're trying to basically, we're reducing all this thing to that, right? So by definition, it's the stuff between the two terminals. It's not a convention, it's a model, it's a simpler model of the stuff that's there. We're simplifying that network. Actually, I guess I'm not sure what you mean by adjacent. Are you saying if you put L equivalent like here, and then kind of drew it like that? Yeah, it'd be the same. Yeah. It's a wire with an inductor in it. If this slides up or down, that isn't going to change anything of the way it actually works. Yep. Okay, no more delays. You have to do example problems. And did I hand those out last time? I want to blame it on you so that I don't have to go get those handouts. Then let me go get the handouts that I just printed again, and I will pull this up so you can get started on this problem. But it's really assignment 8. It's lecture 6, assignment 8. So. Okay, so I expect you to have this one done by the time I get back. You don't want to work on the board today. These are not originally terribly hard. Here they are.
Every time. Why not?
Oh, right on the board now. Why can I go to the? Am I stuck here? Where's my switcher to go to the other camera? Oh, I only have one camera on this camera. Shit, I forgot. I'm so confused. So we are going to expand that. And I just do hold this up. So we're doing the first problem, which is, oh, darn. Can't use this one. Always something. I think I have to use this camera. So this works. Are you doing the same problem? There's a handout here. Mm-hmm. I'm confused on that. So it's 10 plus 3.75 t. When t is 2, that's going to put you at 7.5, right? Or what? It should put you at 17.5. I think you're going too far. You divide by c, it's 1 over c times that. It's 1 over c times the integral. Mm-hmm. Yeah. Yeah, I just so slope from 0 to 2. Yeah, but you got to divide it by c. Yeah, and it's actually, there can also be an initial condition. So if you know the initial voltage, yeah, yeah, there you go. So the integral of all this stuff, but you got to have a 1 over 2. Mm-hmm. Mm-hmm.
Oh, wait, there's a formula. Yeah. C, 1 over C times the over.
Oh, no.
Yeah.
Yeah. Yeah, so this is true, and so v of t equals 1 over c times integral by t. And you can add a v0 to it, so the full equation is going to be, because there's boundary conditions, right? Because when you differentiate,
Oh, V naught.
yeah, so v is 0 plus 1 over c times the integral from 0 to t of I dt. And in region 1, right? And then in region 2, it's going to be in this region, well, it's going to be whatever v of 2 is, right? So you can solve it for here. Then it's going to be v of 2 plus 1 over c times the integral from 2 to t.
Okay.
You know, you only add whatever you're, you got to add this, wherever you are at t, if this is t here, you got to add the integral from this to t. You know what I'm saying? Yeah, so this is definitely a good thing to kind of clarify this. Sorry, say that again?
T equal 2.
Yeah, so up to t, no, it's not only 2, it's just t. Because you want to know as a function of time.
For the first one.
Like right here, when t is 2, yeah, then you do the integral of that whole thing. But if you want to know what it is along the way, you can get a function of time. It's going to be a, it's going to be a ramp. It's going to be increasing, like that. And you can find the slope and everything and make an equation. And that will work if you use t here, right? So this is, so you can kind of qualify this where, this is for, 0 less than t less than 2. Right. After 2, things change, right? And once you get that, you'll get that equation with a t in it, because that's what they have in the answer. The solution is 10 plus 3.75 t volts in that interval. Once you find that, then you can evaluate what is, what is the voltage then when t equals 2, and then that becomes your initial voltage. You really got to do it. So let me stop talking and let you guys do it. So there you go. You found v of 2. Yeah, that is correct. Hmm? Any questions? That should just be 15, right? Is that 15 amps?
Well, I mean, the scales of.
Those are milliamps. Milliamps, right? Milliamps.
So for IDT, then what do you put it there then?
Well, I is just a constant. So it's just 15 milliamps. So you're integrating 15.
Okay. I guess we don't have to have this.
Yeah, you can.
It's kind of hairy.
Well, the thing is, if you've got, what was C again? Was it millifarads?
Yeah,
So you're going to have basically milliamps over millifarads, which is the same thing as amps over farads. So
Okay.
I think, you know, you could just say it's 15 over 4. And then you'll have an answer in volts, right? So you can put the there, 15 there, or the 4 there, or the 4 there, whatever.
And then we're doing like
Negative 10. Yep.
Okay.
Yep. With the initial value of what you figured out for 2 at this question. Yeah, because the voltage cannot jump for a capacitor. Yeah. Yeah, it is because it's a, oops, sorry, because it's a square shape, right? If it was a curve, you know, if it was something like a parabola or something, then you'd have a function of t.
Yeah.
You know, but it's not. It's just a straight line. It's a constant here. So yeah. Okay, let's go through. Yeah, so it's 1 over c times I dt plus v of 0, which they give you in the problem statement. Not in the integral, but after the integral. You know. Yeah, when you're all done with the integration. Yeah, you have that. Yeah. Oh, if you're 2 to 4. Well, this has to be v of 2, sorry. This is a terrible marker. Why don't we get a better one? Maybe I need to get new markers.
Chalk.
Oh.
A little.
Is it better? Yeah. So you could take you got to figure out the result for 2 from. So Matthew found the answer here for 0 to 2 was 10 plus 3.75 t. Because he did v0, which is given as 10, plus this integral. And you did this I is here is 15. There's 15 right there. And you integrate that, and you get 15 over 4 is 3.75. It's just the integral that I just put a t on it, right? Because it's just a constant. Because the 4 there is the capacitor. 15 milliamps over 4 millifarads. You integrate that, you're going to get volts. So now you take this number when t equals 2, which is 17. So you got to change that to 17. Yeah, it's going to be 17 plus. You delete that. No, it's just whatever the initial value is, and then you add the additional area of that you didn't include yet. You've already counted for the area of this stuff, so you don't have it. So you do that, we'll get a new value, right? So he found that it was 17 at 2. So you have to integrate this. So this is v of t again, but it's over the 2 to 4. Mm-hmm. Well, but actually it's t, but it applies for the region from 2 to 4, but you're actually, if you want it as a function of time, you're going to just integrate up to t. And you can change t to whatever you want, but that gives you flexibility t there. And it's a little weird, and I think what's kind of weird is when you have a dt here, and you can have a t here, you know, but it all works out. Okay. Your integrals, yeah. Well, remember, it's pretty easy, right? The integral, if you think about it, right? When you have a constant here, right? The integral of this is a ramp. It's just increasing, and this is like this. Right? I mean, if this is a height of 5, and this is a width of 2, the area is going to be 10, and if it's if this instead of 2, if you just go up to say like t here, the area is 5 times t, right? So that's kind of what we're doing. So if you want to know what is the area that I've, of this curve up to time t, you would just say, well, it's, this height times t. The integral of 5 is just 5t, constant, but you're doing the definite integral, so that doesn't matter.
So for something like
but it's not I, right? The integral of I is not, so I is like this value here. You have to multiply times 2. Yeah, so let me see here. Really? Why don't you take really? Yeah, well, you don't have to do a lot of integrals, and the thing is, this is really, but you got to have to own up to calculus. It's pretty important for other engineering classes.
I would simplify this whole expression.
Well, for polynomials, right? If you wanted to integrate, x squared plus 2x plus 3, this is probably you remember from dx, right? Well, it's going to equal, you raise that x, right? So it's x to the third over 3 plus 2x squared over 2 plus 3x, right? Well, now, what if this was I? Well, it would be I times x. What if this was dt? If this is dt, it would be I times dt, right? Well, it would be I times t dt, right? If this is dt, it would be I times t, right? You get a t there, right? That's why it's I times t. Yeah, so it's I times t, yeah. And in this case, I is negative 10. In this part of from 2 to 4, I equals negative 10, as you saw on the problem statement. And C is 4 millihenries. So it's 10 over 4, because this is actually milliamps. Milliamps over millihenries. Millifarads. Milliamps over millifarads would give you volts. Milliamps times T over millifarads would give you volts. So you don't have to put,
and then add 10, or yeah, that's probably what you should do. You don't have to teach it here. If you think of this as the equation, you do the 1 and 4, then you're going to come up with
so how'd it go? Everything clear? You found what it is from 0 to 2, and then the value at 2 plugs into here to then find the values of it from 2 to 4. So you continue this, gives you that. Very cool, and that gives you 22.5 minus 5 halves, and then at 4 you're at 12.5. From here you're going to go another integral. Oh, and it just stays there, right? Because it's just you're not integrating anything. And then did you just figure out The last one? Oh, over here. So from 6 to 8. Yeah. So now you can sketch it, and that's what you did here, huh? Very nice. Is that all? You guys good? Mason, you got the same thing?
I need to redo it. I just went straight for the area under the and then I tried to solve for T after the fact, and that's just sloppy.
So what did you do? You just
I solved.
I see. And you can do that. And knowing, because you know it's just a linear interpolation. Yeah. Right. But I mean, you could just, I mean, graphically, you could just plot the points and then draw lines between them, and you could estimate pretty closely what it is if you needed to. You know, it depends on what you're after. But yeah.
Looked at that. Looked at the points.
Yeah. 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 That's what you learn. That's a lot of trial and error. Sure.
Right.
Working out okay?
No.
So you got
So
first part is okay.
Yeah. So after you have to integrate this whole thing.
Yeah.
Then you get this is
17.5
well
minus 5 T,
yeah minus 2.5 T.
Yeah.
And then you have to evaluate it. Yeah. Yeah. No, it's not very.
Yeah. Plugging in a T and a T there, but it's
So then this is
so 7.5
minus and then
0.5 T
yeah minus 2.5 T,
minus 0.5.
which is actually a negative.
Yeah.
Yeah, 2.5 times 2, which is 5. So then yeah,
There's a T that's 0.5 T.
oh yeah, T. But
0.5
yeah.
minus 2.5 T.
Yeah.
Yeah.
Wow, that's completely illegible. This keeps getting worse.
Yeah. But that's the point.
So once you get this, you still have to plug in
The range.
Yeah.
Okay. It only applies. You're doing is you're keeping track of the charge that's that the integral of I dt is sort of giving you the charge.
Yeah.
And V equals Q over, or V equals Q over C.
Yeah.
So you're integrating the charge, current to get the charge, but you only need to integrate the part from the new region that you're looking at. Because you want to find what's the additional charge you got over this region. You know, and that's what you're integrating.
Oh, and nothing showed up here because I got a 0 bottom.
Right. That's why there's a 0 there. But for this, you got to do this too.
All right.
Yeah. Well, we've come to the end of another productive hour of. Yeah, that's half of it was lecture. Are there anything we should look at in the remaining? Let me just see. I'm going to stop the video. So this one, 2 capacitors are connected to a 100-volt source. Find the energy stored in each capacitor if they're connected in parallel or in series. Yeah. So in parallel, it's pretty easy because you just add them up. You got to do each capacitor, so yeah. But that's stuff that shouldn't be too hard.
Yeah.